Hallia College math students. I'm going to complete a few examples from the textbook. I want you to make sure that you try these before watching the video. So if you haven't tried V2.4 here, which is in the textbook, and it's on page 18. So we're going to try this one. Okay, so this example here I'll do as blue. So we're going to try this one here at the top of page 18, and we're going to have a go at the kitchen design one as well in this video, so try that one. Then we've got a challenging one here. I'll do this in red just to show this is a challenging one. So if you're not, we're going to try this one first, but if you're not sure how to do it, that's okay. You can just ask me in class for some tips, or you could watch the video. So it's mainly about at least reading the question first before you watch the video and seeing if you can do it. If you can't do it, by all means ask for help or just watch the video. Don't worry about the martini glass one, 2.5. Skip over that. But I want you guys to try the flag one here, which is at the bottom of page 19. Don't worry about the drum one. Scribble that out. We're not doing that one. Okay, so pause the video now if you haven't tried these and have a go at these examples. Then I'll solve them on this video. Okay, here we go. So we're asked to make some predictions about the perimeter of this perimeter and area of this shape, this trapezoid or trapezium as they say here. Okay, so go ahead and calculate the perimeter and area. So perimeter, if I add up all the sides of this, I should get 46 centimetres. And the area, so you may remember from earlier in the unit the formula for the area of a trapezoid. We take the average of the top and bottom side lengths like that and then multiply by the height of the trapezoid. So if we do that calculation, we get 104 square centimetres. Okay, so we're asked to make a prediction about what the perimeter and area will be for a scale factor of 2.5. So we know that perimeter will increase at a linear rate. So all we need to do is multiply this answer by the scale ratio. For the area, however, it is at a quadratic rate, which just means we need to square that scale factor and multiply by the area. Okay, so for the perimeter, the new perimeter of the shape is going to be, what is it? It's going to be 2.5 times that amount, which if we multiply by 46 by 2.5, we get 115 centimetres. That's the new perimeter. The new area is going to be 104 times 2.5 squared, which gives us 650 square centimetres. So those are our answers for the new perimeter and the new area. So once again, we're asked to find the dimensions of this new trapezoid, which is going to be 2.5 times the size of this one. I'll make a big looking one here, just really quick, rough one. Okay, so everything's been scaled up by 2.5, so all the different side lengths will be 2.5 what they were in this diagram here. So 7 by 2.5 is 17.5 on this side. 10 here and 10 here, they're both 2.5 times that is 25. And 19 times 2.5 along the bottom is 47.5. Oops, daisy. And up through here, the new height is 20. So to confirm this, well, if we added these all up, these side lengths, would we get 115? So 25 plus 17.5 plus 25 plus 47.5. Check it out. I'll just check it on the calculator. We add those up and we do get 115 for the new perimeter. It matches that answer there. What about the area? A half times the base length plus 47.5 at the top times by the new height 20. So chuck that into your calculator, and do you get the same area as before, 650? Let's find out. Yep, and that works for me, so that matches as well. So in that last part, finding the dimensions and just confirming through some calculations there. Okay. Kitchen design. It's drawn to a scale of 1 to 50. How many times is the area of the kitchen bigger than it appears on the plan? Well, if we're talking about a length within the kitchen, like a bench that was 1 metre long, so if on the plan it was, so there was a bench on the plan that was 1 centimetre long, not 1 metre long, 1 centimetre long on the plan, then in real life it would be 50 times longer than that. It would be 50 centimetres. But this is the area that we're talking about here. So remember, this increases by the scale squared. Okay? And that means our scale is 1 to 50, so we're scaling up. The scale ratio is 50. I suppose what I was talking about earlier is actually dividing the two numbers, like to get the scale ratio 50 over 1. I know it still gives 50, but if that number there, 1, was some other number, it can get a bit trickier to find that scale ratio. That's how we do it. Just divide the number on the right by the number on the left. And this gives us 2,500 times bigger. Wow. So the area is 2,500 times bigger in real life than what it appears on the plan. Okay, now this sail border question. This is interesting. This is a tricky one. I want to use a bit of a picture to help here. I suppose sails are shaped like triangle type shapes. Okay, so there's the small sail, and the small sail has an area of 4.2 square metres. Okay, now a slightly larger sail, the medium one, now that is scaled up by 20%. So this is a tricky one, and we deal with this percentage increase decrease later on in finance. I'll just make this sail look a little bit better. It's 20% bigger than the previous one. Now, in fact, this we could represent with this scale ratio of 1 to 1.2. So if we want to increase something by 20%, we multiply it by 1.2. So that's where we get that scale from, 1 to 1.2. So that means our scale ratio is, we're scaling up by 1.2. So to get the area, we'll take the original area of the smallest one and multiply it by 1.2 squared. So there's our scale ratio, 1.2 squared. So that gives us 6.048 square metres for the medium-sized sail. Okay, now the large sail is scaled up by 50%, so it might look something like this. Now, using what I talked about here, you might be able to predict what the scale ratio is for this one. So 1 to 1.5. So if we wanted to scale up by 50%, we multiply by 1.5, and that increases something by 50%. So we will explore this percentage increase decrease further when we get to the finance unit. So if you're not quite getting it, it's a bigger part in the finance unit than it is in this measurement unit, but that's how it works. So this gives us 9.45 square metres for that one. Right. We're going straight to the flag. This is a tricky one, involves some algebra. I'm going to do a flag more like a golf flag. Normally our flags these days are rectangular. It's an interesting thing that most countries' flags need to have that rectangular shape. But there are a couple of countries that have that they've pardoned from doing that. Maybe you could look into finding out which country doesn't have a rectangular shaped flag. Anyway, this flag here has an area of 3.5 square metres, and it's going to be enlarged so that its area of this new flag is 6 square metres. So what is the scale ratio? That's the question. Now let's have a letter for scale ratio. I'll call it the letter R. Okay? So using some algebra here, and I know you probably don't like the sound of that word, but it's not that bad. It's a very useful mathematical language. We know that if we take the original area to turn it into this new area, we need to multiply it by the scale ratio squared. So 3.5 times whatever the scale ratio squared is will give the new area. Now rearranging to get R squared on its own, 3.5 is multiplying by R squared, so it goes over the other side and divides. And then we want that square to come over the other side as well. What's the opposite of square? Square root. So R equals the square root of 6 on 3.5, which gives us 1.3 and some other stuff. I'll just check it again. 6 over 3.5, 1.309 ... You could just round to 1.3 if you like. Right, so a tricky one to finish there. And those are some good questions. These are really quite tricky questions. So if you can manage to do these, then you're definitely working at a really high level.